So this is going to be a tutorial on how to model and simulate a wing with aspect ratio of 10 in XFLR5. So let's go ahead and get started. Open that application up. We're going to go to Module tab here, go to XFoil Direct Analysis. We have to do the 2D stuff first to gather like data for our 3D analysis to interpolate from. And we're going to be using the 2415, the NACA 2415 airfoil, generated with about 200 panels. Then we can go over here, hit OK, and then we're going to run a batch analysis on this. So we need to make sure we're going from alpha -5 to 15 if we want, those same values for our actual wing design and like analysis. And then we're gonna have to make sure at about 15 meters per second, we're going to get around a number of around 3.3 million. So I just generated a bunch of different ones. You can see 100,000, 250, 500, 700, and it goes all the way up. Kind of clusters around that 3.3 million Reynolds number and then goes up as well. So yeah, you just want to make sure you have a bunch of data. This is probably overkill, but to each their own, right? So we're going to hit analyze here. See these polar graphs filling out. Okay, now that the analysis is completed, we can go ahead and close. And we can kind of leave this module now. We're going to go over to wing and plane design. And then over here, we're going to define a new plane. I'm just going to name it AR10 for aspect ratio 10. And then we're going to go ahead and just delete the fin and elevator because we're really only interested in the wing design here. Let's go. For an aspect ratio of 10, we're going to need a wingspan of 10 with our chord length of 1. So we go over here, make those 1, and then I'm going to set this second y coordinate, so the y goes this way to 5, and that's going to make our total wingspan 10. And then set this offset to 0 because we're really only interested in the aspect ratio here. And we're just going to click here. It would, if you had multiple foils, give you a drop down, but we only have one, so it's going to give us that option. You can kind of see here. I'll make sure that offset's 0. You can see here now we have like a 3D shape generated here. And now I need to just click save, and then we're going to go here, define an analysis. We're going to use fixed speed at about 15 meters per second. And then just make sure that the analysis is on LLT, so lifting line theory. Then everything else looks good. Hit save here, and then we go over to this side. We're going to be sequencing from -5 degrees to 15 degrees with increments of 1, just like our batch analysis on the 2D airfoil. Then let's click analyze, and then I actually spent a long time trying to figure out why this wasn't working. Like I could only see, uh, I didn't see a CL value for the longest time, but it's right there. And all the other stuff, so you have your Oswald efficiency number versus alpha, CL versus alpha, CL versus CD versus alpha, and then CD versus alpha. And to kind of export these plots, you're just going to go here, right click them, go to current graph, and then export graph, and then you can pick a folder, and then it'll be sent as CSV file, which you can import directly into Excel. Very convenient. And then if you needed to like change what's on this graph, just double click it. I can change it to, let's say, CL over CD. There we go. So we have that graph now. And then you could export that and it will give you these values in a CSV file. And then to get the like variation of the local lift coefficient, induced angle of attack, induced drag coefficient, all of that along the span of the wing. You're gonna go over to this tab, the op point, and then we want it at 5 degrees. You can use any angle, but I'm just gonna go ahead and do 5 degrees. And then, so this graph is the induced drag over the span from -5 to 5 meters. If we wanted to change this to say do local low lift coefficient, we just click that, go over here, and there we go. And to plot these, so we can also do the total angle, which is just effective angle of attack, and total or uh, induced angle, induced drag. Yeah, so these four really are important ones: local lift coefficient, total angle, induced angle, and induced drag coefficient. But if you wanted to export these into a plot, you go over here, go to current graph, export graph, and again, you'll be able to send it out as a CSV file, which is very convenient. Yeah, that about wraps up our tutorial. Have a good day.